In this video, we are going to talk about Laplace transformation. The knowledge of Laplace transforms has in recent years become a necessary and essential part of the mathematics background required for engineering students taking advanced engineering mathematics. This is because the transform methods provide an easy and effective means for the solution of many problems arising in different areas of engineering. Let me introduce to you the person behind this method, and his name is Pierre Simon Laplace. Laplace was a French mathematician, astronomer, and physicist who applied the Newtonian theory of gravitation to the solar system. He played a leading role in the development of the metric system. The main idea behind the Laplace transformation is that we can solve an equation containing differential integral terms by transforming the equation in t space to one in s space. That's why this method is useful and powerful for solving linear differential equations arising in engineering mathematics. It consists essentially of three steps. In the first step, the given differential equation is transformed into an algebraic equation, which is called a subsidiary equation. Then, this subsidiary equation is solved by purely algebraic manipulations or simplifications. And finally, the solution of the subsidiary equation is transformed back so that it becomes the required solution of the ordinary differential equation. Now let's talk about the definition of the Laplace transform of the function f of t. The Laplace transform of f of t for t greater than 0 is defined by the following integral defined over 0 to infinity. So this is the operator of the Laplace transform. The Laplace transform of the function f of t is equal to the integral of the kernel function e raised to negative st times f of t dt with limits from 0 to infinity. The resulting expression is a function of s, which we write as f of s. In words, we say the Laplace transform of f of t equals function f of s. Now let us derive the Laplace transforms of elementary functions. We start with f of t equal to 1. Using the definition, says that the Laplace transform of f of t is equal to the integral of e raised to negative st times f of t with respect to t with limits from 0 to infinity. Now we plug in this given equation, the value of f of t. In this case, we are solving for the Laplace transform of 1. Using integration, we can use a formula for integrating exponential function. So we let u equal to negative st, and then we differentiate to make sure that this is satisfied. So du is equal to negative sdt, and then we plug in the given integrand. We now have negative 1 over s integral of e raised to u du. So maybe you're asking why negative s. So this is a neutralizing factor coming from this substitution. So now we can determine the integral of e raised to u du, which is e raised to u, and then we apply the limits after we bring back the original value of u, which is negative st. Then we apply the limits. So upper limit minus the lower limit, 1 over e raised to infinity is equal to 1 over infinity minus the lower limit, so 1 over e raised to 0, which is equal to negative 1. That's why we have negative 1 times negative 1 over s. We now have the Laplace of 1 is equal to 1 over s. Now let's proceed to another derivation of a transform of an elementary function. So f of t equal to e raised to at, where a is a constant. Now we use the definition in deriving for the transform. So we have the integral of e raised to negative st f of t dt. Okay, since f of t is equal to e raised to at, we plug it in here. We now have integral of e raised to negative st times e raised to at dt with limits from 0 to infinity. Since these are exponential functions, we can rewrite this into one exponential form, which is e raised to at minus st, just using the law of exponents. And then factoring out negative t in the exponential function, we have e raised to negative times the quantity s minus a times t with limits from 0 to infinity. So the same idea in solving for exponential functions. So we'll let u equal to minus s, or minus the quantity s minus a times t, and then differentiate this u. We have du equal to negative times the quantity s minus a times dt. Now you plug in here, we now have the result, which is negative 1 over s minus a times the integral of e raised to u du with limits from 0 to infinity. Okay, so integrating e raised to u du, we have e raised to u. So before we plug in the limits, we need to bring back the original value of u, and that is e raised to negative times quantity s minus a times t. So upper limit minus lower limit, we have, what we just did here is to make exponential function positive with the positive power. Now we have the upper limit, so 1 over infinity, or e raised to infinity is infinity, and e raised to 0 is 1. That's why we have this result, negative 1 times negative 1 over s minus a. Then we have the Laplace transform of e raised to at equal to 1 over s minus a. To learn more about the properties of Laplace transforms and the complete list of transforms of elementary functions, please watch the next video.